Hello, my name is Jason Ngo, and today I'll be discussing to you the concept of fractals and how it is made. Now, for a brief history of fractals, Benoit Mandelbrot was born on November 20, 1924 and died on October 14, 2010. He was a French-American mathematician who discovered the concept of fractals. Now, what are fractals? Fractals is a mathematical shape that is infinitely complex or a pattern that repeats forever, and every part of the fractal, regardless of how zoomed in or zoomed out, will look very similar to the original fractal. So let's take these three examples. As you see, the patterns keep repeating themselves as they go smaller and smaller. These patterns go on infinitely and continuously repeat themselves, thus creating fractals. Now, let us move on to the applications in the real world. Now, the concept of fractals has always allowed us to understand the large-scale structure of the universe because it has always been here since the beginning of time. For example, in nature, it can be seen in rivers, lightnings, and clouds. Now, as you can see in the first photo in rivers, the river follows a branch-like pattern creating fractals as well as the lightning. And the clouds create circular patterns which can also be considered as a fractal. It can also be seen in our technology through our antennas and cell phones. And this fractals has always allowed us to receive all kinds of waves and frequencies that we use every day, such as the FM radio waves and TV wavelengths. Now, let us move on to its characteristics. The first characteristic of a fractal is called recursion. Fractals typically repeat an action to a figure or a formula to get a continuous set of new results. Let us take this video as an example. As you can see, the figure always follows a pattern. A triangle is always put on the top, left, and right of the previously made triangle and infinitely repeats itself, thus follows the concept of recursion. The second characteristic is called self-similarity. Fractals are always perfectly self-similar between the original figure and the smaller copy of the original. Now in this video, the figure, as you continuously zoom in, never changes its shape. That implies that the smaller figures made is the same as the original figures made seconds ago. Now, the last characteristic of a fractal is called fractal dimensions. It is known that we live in a three-dimensional space, which are the first dimensional, second dimensional, and the three-dimensional. But fractals can also exist in a non-integer dimension. What does that mean? As you can see, the two photos on the left are famous fractals, while the photo on the right is just the simple three-dimensional plane that we live in. The first photo on the left is the Coke snowflake and lives in the fractal dimension of 1.26186, which means that it lives in between the first and the second dimension. But it does not mean that it lives only in the first or second dimension. The next fractal is called the Menger sponge and lives in the fractal dimension of 2.726, which means it lives in between the second and the third dimension, but it does not mean that it lives in the second or the third dimension itself. You will be discussing more of this later in the video. Now, let us move on to the different types of fractals. The first type of fractal is called the iterated function system, a method of constructing fractals that are often self-similar and are commonly computed and drawn in 2D. The most notable examples of which are the Sierpinski triangle and the Coke snowflake. The second type of fractal is called escape time fractals. It is a fractal that exists within the complex plane which are generated by a formula on each point in a given space using the formula Zn plus 1 equals Zn raised to 2 plus C. As you can see, it is a very complex form of fractal which creates many different types of patterns as seen in the Mandelbrot set and the Julia set. Lastly, L-systems is the last type of fractal. Originally conceived as a mathematical theory for a plant development, follows a branch-like pattern that is most commonly seen in trees and plants. As you can see, the branches and leaves of the two photos follows a certain pattern creating fractals. Now, it is time to make our own fractal. Now, we must remember these three characteristics as these three are what defines a fractal and make sure that the fractal we make meets all these three criteria. And because of this, I'll be making an iterated function system type of fractal as it is the most basic and simplest way to make a fractal. So, the first step to making a fractal is to find a shape or a figure as your base. Now, we can use a square, a rectangle, a triangle, a polygon, or whatever you like. But for me, I'll be using a circle. The second step is to make a pattern and set it as a rule to follow. So here are my rules. I have to set 3 circles, one smaller circle on the top, bottom left, and bottom right of the previous circles made. Now, the size of the newly made circles are to be half of the previously made circles, which means that the previously made circles must be twice as big as the newly made circles. Here you can see that the green circles are the newly made circles and follows the pattern I set. And the base figure is twice as big as the newly made circles. Now, if we move on to create the pattern again, the green circles become the previously made circles and the blue circles are now the new circles. And as you can see, the blue circles still follow the pattern I set, and even if the figure gets smaller, the smaller figure still looks exactly the same as the original figure I made a while ago. Now, the last step is just to repeat it all over again. Now, if we move on to create the pattern again, there you go. You can see that the blue circles are now the previously made circles and the orange circles are the new circles. And as you can see, the pattern that I set is still there, and the smaller circles are also half of the previously made circles. Now, how do we know if it really is a fractal? The answer is fractal dimensions. Fractal dimensions will help us determine the amount of newly made circles that will be made in a certain order. So the first step is to examine the differences between the base and the newly added pattern. So the base, I will call it order 0, and the added pattern will be order 1. So now, to solve for fractal dimension, it's just only the logarithm of the number of self-similar pieces found and the logarithm of the scale. So the scale, as you can see in the bottom figure, is just the size between the base figure and the self-similar pieces found in the first order. So as you can see, the scale there is just 1/2. So the base figure is twice as big as the self-similar pieces found in order 1. So for our given, the number of self-similar pieces is 3 because we have 1, 2, 3 circles, and the scale will be 2 because the base is twice as big as the self-similar pieces. So now the solution is the logarithm of 3 over the logarithm of 2, which will give us a fractal dimension of 1.585. Now we know the fractal dimension. Step 2 is to solve for the amount of self-similar pieces found in each order using the fractal dimension. Now, let us check our answer first. To solve for the amount of self-similar pieces, it is the scale raised to the fractal dimension. So we are already given our fractal dimension of 1.585, and we already know that the scale from order 0 to order 1 is 2. So the solution becomes 2 raised to 1.585, and if you input that in the calculator, the amount of self-similar pieces should be 3.00. Now we know that we are correct, as in order 1 there is only 3 self-similar pieces. Let us try another example. Let us try to compare order 0 to order 2. Now, we must get the scale first because we do not have that. So we must compare the size of the base compared to the scale of the self-similar pieces. Now, from the bottom figure below, we have learned that the base is 4 times as big as the self-similar pieces. So that should be our scale, 4. And now, the fractal dimension still remains the same in 1.585. And so our solution becomes 4 raised to 1.585, and the amount of self-similar pieces we should get 9. Now let us check. Now the amount of blue circles we have in the figure is 9. So now we know that we are indeed correct. Thank you for watching, and I hope you have learned a lot today about fractals.